In the interest of, I always forget to check with you. We're gonna get started. Welcome to the AstroAI launch talk. We have two speakers today. We're gonna tell us about very interesting stuff. So the first speaker is Constança Tropa. Constança is completing a master's thesis here, working with Carol Lastro and Dan Eisenstein. And Constança has been working on very interesting, generative models for cosmology, in particular to, understand the contribution from peculiar motions of galaxies to the general framework of measuring cosmological parameters. And Constança is going to be our first speaker. She's going to get a degree from ETH in Zurich, and you will see applications from her because she's going to be looking for grasp. So Constança, the floor is yours. Thank you so much.
Thanks, Rafa. Hi, everyone. So yeah, that was a pretty good introduction. I need to introduce myself again. So yeah, I've been here for 6 months. I'm going to leave in a couple of weeks, but I'm very excited to show you what I've been up to. And even though Carol's not here, I wanted to give her a shout out because she's very good. And if you ever need to talk generative models, definitely reach out to her. So basically, my project is a cosmology project, which means that, we want to learn about the statistics of the universe on very large scales. So what you see here is the dark matter field, a distribution of how dark matter looks like in 3D in our universe. The problem is we can't really measure dark matter, right? And so what we actually do is we look at galaxies to see the underlying field of dark matter. The problem is that galaxies are actually bias tracers, meaning there's not a one-to-one correspondence. So the first thing we need to solve when we look at it is to understand how this bias works. On top of that, because of the expansion of the universe and the peculiar velocities of the galaxies, what we measure, the redshift we measure, isn't actually the true distance, but rather kind of a distortion of where galaxies really are. So basically, because of the way the light is emitted and what happens until it reaches us, which is first space expands, but also galaxies, depending on how they're moving along the line of sight towards us or far away from us, then we measure a bit of a different signal, okay? And the signal that we measure, this distortion, is what I'm going to be kind of talking about today. So it's really important that you understand that because of how galaxies move, what we see is a distortion of what is true. And the goal is to learn these peculiar velocities so that when I want to look at the redshift surveys of galaxies, I actually can say, oh, the galaxy is here, and not, oh, the galaxy looks like it's here, okay? So basically, I learn the peculiar velocities and I can go back into real space, learn the distribution of the galaxies, and therefore learn the distribution of the dark matter, which gives us all types of information about the universe. Okay, the thing is, the peculiar velocity is also dependent on the dynamics of our universe. And so what we often do when we measure peculiar velocities is to actually assume things about cosmology. In my project, I don't want to do that. I want to marginalize over parameters, meaning that I don't want to say, oh, omega m sigma 8, these parameters that describe the universe are a certain value, but rather I want to give my model the chance to figure it out for themselves, okay? So there's kind of two parts of my project here. The first is parameter inference, and the second is this reconstruction of the peculiar velocity fields. Now, I already talked about parameter inference a little bit a couple months ago here, so I'll be focusing more on the second part because it's a little bit more interesting, but feel free to ask me questions about the first part as well. So basically, what's happening here is that we are looking at posteriors, okay? So we're not actually, I don't say, oh, my parameters are this. I say my posterior, what is the probability of my cosmological parameters and my linear bias to be a certain value given a density field of the galaxies in redshift space. I say, what is the posterior of the nonlinear velocities given my fields of galaxies in redshift space, my linear velocities, and my cosmological parameters. And this is kind of the golden thing, which is ultimately what I want to do is I start off with galaxies in redshift space, which is what I can measure. And I want to learn both the velocities and the parameters. Okay. Why machine learning and why simulations? All of this is highly nonlinear. Okay, so it's very. First of all, we only have one universe. So for me, given that I want to actually look at the cosmological parameters, I want to have a set of simulations so that my model can learn what happens when we tune these parameters. And second, because it's very nonlinear, simulations are a good way for us to see what happens at late times. I'm using QUIJOTE N-body simulations, which is dark matter only, and I'm basically painting galaxies onto subhalos. And the reason why machine learning here comes super handy is because I'm using fields that are 128 cubed grids. So these are 3D fields that I'm looking at. And 128 cubed turns out to be 2 times 10 to the 6th order of magnitude. So this is highly multidimensional. This is very high dimensional. And so when I want to actually sample from my posterior, what I'm doing is I'm sampling 128 cubed values, right? And so we're going to kind of bypass that by using something called diffusion. Okay. So there's different tracers that I'm using to check the cosmological parameters. This is the part that I'm going to go through a little bit more quickly. But basically, what I want to do is check what happens when I take different things that my model can learn on, and how well does my model learn what these values are, which are the cosmological parameters, and the bias, which is again this relationship between dark matter and galaxies. Okay, so I start off with the power spectrum. The power spectrum, it's a statistics of the universe that we can take on different scales. And in blue, you'll see the power spectrum in real space. And you see the orange line, this is the power spectrum in redshift space. So here already we see this effect of this distortion. And even though you might think that it's actually really annoying that we have these distortions, it turns out that our model likes them because it learns information about the universe and about these parameters, which is exactly what we want. So we're actually exploiting the redshift space distortions rather than trying to eliminate them. Then we go on to a little bit more complex fields. So those are basically just one-dimensional sets of data. And then I go on to try different density fields, matter, galaxies, and galaxies in redshift space. And finally, I also add the peculiar velocities to see if by then my model, which now has the information basically fully to correct for redshift space distortions, if it can learn more constraint parameters. So overall framework. And how do I do this? So I wanted to put some machine learning here because I think often we talk about the physics, but all of you either are cosmologists and know this or are not, and then you care more about AI. So what I'm doing is I'm minimizing the negative log likelihood function. So that's here. And if you look at this expression, you'll actually see here that I am using a normalizing flow. And I'm putting this here to show you that there's different packages that you can use. So if you're talking about normalizing flows, you don't always have to reinvent the wheel. I literally just use something that's been done for me, because the point here is not for me to learn how to build a normalizing flow, it's to actually use it and see what happens. So there's this Google package that has all these different types of normalizing flows there, if you want to try it out. And then the normalizing flow actually takes as input not the raw data as we know it, but something kind of in a latent space, what we call it, where basically here, again, I'm using just a package, R3D18, which is a package that builds an 18-layer ResNet, okay? So basically this means that the data I give it goes through all these convolutions and transformations so that what my normalizing flow gets is already something that is informed and not just raw data. So this also makes my training a lot easier and faster. Okay. Oh yeah, I always try to put things up because people in the back can never see what's under here. So this is what I'm talking about. And yeah, I mean, my results are a little bit different than the last time I presented them. Because
Is it better than last time?
as in different. The surprising thing here, so basically here I'm showing you statistics in real space, and here I'm showing you statistics in redshift space, and here we'll look at after. But you'll actually see here, for example, that the power spectrum, which is in blue, which is this one-dimensional statistics, is being better and more constraining as the 3D full galaxy density fields and redshift space. So this is something that wasn't the case before, but I was doing something wrong and now I fixed it. It's not unheard of that actually a model can just learn more about the power spectrum, especially for omega m, which is how much matter is in the universe, because it's a very simple thing to learn. Whereas actually, the model has a hard time figuring out what happens when you have all the information. But I think if I put these two together, it will be a lot better. So that's something that I'm still figuring out, okay? But just so you know, it's not unheard of that this has happened. Like, there are papers with QUIJOTE N-body simulations that have the same results. What is way better than before is that when I add the peculiar velocities, so I want you to compare basically the orange and the green actually does really help us in my model to learn how to correct for redshift space distortions. So I'm pretty happy about this. Yeah, so the one thing I can do now that we have better GPUs is to actually go on and train on 256 cubed grids. So let's see how much.
Do you clarify again what are the three different ones, the three curves here? The orange one is what?
The orange one is galaxies.
Okay.
The blue one is galaxies. The blue one is galaxies. The orange one is galaxies in redshift space, and the green is galaxies in redshift space plus the peculiar velocity.
So the galaxies and redshift space is sort of more on target but less constrained.
Yes.
The green one looks more constrained, but also seems to have added a little bit of a bias,
Yes.
correct?
Yes.
Is that problematic for you or not?
For now, not super much, because it is still right. Like, I'm showing you one example here, but overall the loss is much lower here. So if you go through all the samples, it's not the case that it's always biased. Yeah. I just picked this example because the real value of sigma 8 is kind of 0.8 or
Yeah, on the other hand,
And
it only seems to be a case only for sigma A, right? Like for the other two,
yeah.
it's actually better. So, yeah.
Okay, so yeah, and then putting these statistics together and see what happens. Now, what I want to go through more slowly is this peculiar velocity reconstruction, because I see that a lot of us in astrophysics have this desire to know what happens in 3D. And usually reconstructing things is very, very expensive. And diffusion models are kind of the holy grail if it works. And so for those of you who don't know it super well, because I think it's an up and coming generative model, I want to explain it to you a little bit better, because it also took me some time to actually understand step by step what's going on. So I'm going to try and actually explain things and not just say these like big words that in the end you just leave just as confused as you came in. So goal now is to say, okay, I assume I know the cosmological parameter, and I want to reconstruct my peculiar velocity fields, okay? Now you'll see here that I have an NL for nonlinear and a lin for linear. The reason why I have this is because on large scales, we actually already have a theory that tells us what the peculiar velocity is, okay? So the goal here is not to go from complete noise to peculiar velocities, but rather to start off from something that we already kind of know works really well, and then put more detail onto it, okay? So not super important how exactly, but here you see that the velocity is related to the density field. So that's how I get the true velocity, the linear velocity. I take the galaxy density fields, okay? This, however, works for the actual density field, which is the matter density field. And so here is kind of where this bias that I was telling you about comes into play, okay? So I'm giving my model a value for the bias because what I have is the galaxy density field and not the dark matter density field. At the bottom here, you'll see A, H, and F. This is cosmology jargon, but basically this tells us about the properties of the universe. And these are numbers. F is the growth factor, which can be parameterized by omega m. And so, yeah. And so this is, again, how the cosmological parameters influence my model, okay? It's very important that you understand this dependency of one thing to the next, because, yeah, like, that's the whole point, okay? So this is how my parameters that I, in the first part, want to figure out what their value is, how they come into play here. And now the goal will be to go from this to the true nonlinear velocity. So you see here that there's a lot more fine resolution, let's say. And so what I want is my model to learn how to go from that to this. Okay, this is from the simulations, and that is a linear theory result. Okay. Yeah. Okay. So this is the flow matching model kind of go to let's say, I don't know, scheme. We start off with what I call x0, which is my linear velocity field, and the target is x1, which is my nonlinear velocity field. Now it's not actually the fields, it's the distributions, right? It's the posteriors. So what we want is to go from this initial distribution to a final distribution. And the thing is, instead of me actually going from distribution to distribution, I'm learning the instantaneous flow that, if integrated, would give us the distribution. So basically, if at any point I want to sample, then I take a flow that I learn, which is basically the mapping, and I can use that to sample, instead of actually learning how to transform the field itself. I learn how to transform the distributions and how the instantaneous rate of change has to be so that I go from one to the final. So this is a lot of words. Conditioning just means that this is extra information that I give my set. So I have my linear velocity field, but how does my model actually learn the nonlinear velocity field? And that's by me giving it the redshift space galaxy distributions that we have. That's something that we measure. Okay. More concretely, what happens is we take a time t, random between 0 and 1, where 0 corresponds to our initial time and 1 corresponds to our target final time. And I do linear interpolation of the fields. So basically, really, x0 and x1 are just my fields. And I take a time t and I linearly interpolate and I get a field. Okay, that's my field x of t. For that time, I compute the instantaneous flow, which is just the derivative of this. So for those in the front, I can see this thing down here. My ODE that I'm putting on the screen is basically the derivative of this. So I'm talking about a rate of change, right? This is what I want to learn. So basically what I do is I predict this flow. And we often say flow velocity. I'm only using flow because I'm using velocities and I don't want you to like put these two together, okay? So I'm learning a flow, which is this instantaneous rate of change. And I'm comparing it to the true instantaneous flow that I know is true because I linear interpolate. And so that part is what I'm using a ResNet for, okay? And then I wanted to show you once here actual code of how this works, because it's really not very complicated, but it seems like it. So basically, I literally sample xt by linear interpolating. I compute the difference between x1 and x0, which is actually my derivative. And then I have a velocity model that I will show you, which is my ResUnet, that gives me a v, which is just the flow. And I compute the loss, which is the difference between the true and the predicted. So it's a very, very easy loss. And this is how my model, what my model learns, okay?
So just to reiterate, that's not the velocity field of the galaxies, but the velocity of that will transform your base distribution to your actual posterior.
Yes.
Okay.
I call it here, however, velocity model because I'm modeling my velocities in the end, my true physical velocity fields, right? But I'm basically doing transformations. I'm giving it to a reslet, and the output will be the prediction of my flow. So this is what a U-net looks like. And I have residual layers. But basically what happens is my input is going to be my interpolated field, okay, that I did with linear interpolation, x of t. And then I do encodings and decodings. By the end, I will have the same dimensionality, but this is no longer my physical field. I'm not trying to predict my physical field. I'm trying to predict the flow. Okay? And the reason why we do this is because if we go down and then up again, first of all, we need the same dimensionality for the sampling, which I'll show you in a second. But also this way, we actually extract information on all scales. Okay? Because we're pooling and we're convoluting. So basically, the best part about diffusion models is that once you have your trained flow, your model that predicts your flow, if you want a sample, you just extract it. Now, I thought this would be faster than it actually is because doing integration in the end is still a computationally heavy, yes.
What's the dimensionality of your velocity field of your flow?
Of my flow?
Yeah.
It's going to be also 128 cubed times 3. Exactly. So this is going to be my final target field, right? And this is going to be my starting point. So what I need inside of here has to be the dimensionality of my field. Yeah. So basically, in my case, I'm just Euler integrating. But you can do all types of fun things with neural ODEs and stuff like that. And this is what I have. So basically here is just one example. This is the predicted field, and this is the true field. And I think it's hard to see how it really changes. So I have a small video where you can see that now I have lots of different samples that mostly are very similar in places that we know are right, but then they have this uncertainty around the places that are not so obvious, right? So it's kind of, if you compare linear theory, you're getting detail, and around the regions where it's less extreme, you're getting this variation. So the point of this is now I can get many, many samples of my field, and I actually am doing this probabilistic reconstruction. Instead of saying my velocities are this way, I say my velocities are this, but I have an uncertainty around them. And so when I go back into real space, I have an uncertainty on the positions, which is something that we want in physics, right? So we don't want to say, I know for certain this is the way things are, but rather, actually, I can take really many samples, and they kind of all align, but they're different variations, right? So the way I sample this is by adding a little bit of noise to my initial field, and then I'm sampling. And then I'm integrating over this initial field with a little bit of noise. Yeah, so the mean prediction. Yeah.
Sorry, but these are now the actual peculiar velocities that you're predicting?
Yes. These are the peculiar.
Sorry for my ignorance, but is there a reason why there seems to be like parcels of these things that have higher positive velocities and then other parcels that are negative? So were you expecting them to be completely random, or is the structure telling you something?
The structure definitely tells me something. This already basically tells me the structure, right? This is the gradient. The gradient of this will be the density field. So definitely there's structure because velocities move depending on what's around them. So from the density field, you get velocities. You are expecting them to move kind of coherently. If you have, for example, a big mass somewhere, you're expecting them to move maybe around them. Now, what I can say about these dots that I didn't mention because you're not cosmologists, but if you're asking, here you can kind of see that there's like a super, super negative velocity in something that almost looks like a void, almost looks like zero velocity around it. And this actually is the redshift-space distortion. So if you have an object that is moving very fast in your direction, when you measure it in redshift space, it will actually project as if you're seeing it in this place where there's nothing, but it's actually this effect of the redshift space distortion along the lines. Okay, so these outliers are exactly kind of what we're looking for. And this is what I'm hoping my model will learn, that if I have a velocity that is kind of random in the middle of nowhere, it's probably because my density field behind it is very high. Yeah, and then down here is proof that there is change, even though like they look very similar. Because when we look at the power spectrum, this is plotted with the uncertainty, 1 sigma, but it's very, very low because I'm doing 3D fields, and the statistics are just very consistent throughout, which is actually a good sign. So this is the predicted and the true power spectrum in X direction, which is our simulated line of sight, meaning our redshift space distortions are along that axis. Here you can see the cross correlation, which maybe means a little bit more to cosmologists, but it's basically checking how well do the predicted and the true fields kind of align with each other on a pixel level. And here is for all 3 directions. Now, I was expecting already that in Y and Z direction, you will see that the cross correlation is a little bit higher than in X, which is very much expected because there we don't have the redshift space distortion. So it's easier for my model to just learn from the density field itself. And finally, here is the magnitude. So overall, we're doing pretty good, I would say. Now the goal is to, here it's just samples of the velocities, true versus predicted. They are okay, but these are not very many samples. I didn't have a lot of time. I have to take way more samples, and yeah, but basically you can see here that you have some uncertainty in the velocities, and this is exactly what I want. I want to have velocities that then I can tell the position of my galaxies with certain uncertainty. Okay. So yeah, and then the final thing I wanted to talk about is when you do a unit, think about how many layers you actually need. Because what I figured out is that you actually don't need to pool that many times in my case, because you already have the large scale information from the linear theory. So all this extra pooling is giving you information that you have from the beginning. So this is an example of how you can kind of model your architecture based on the actual physics that you're looking at, and not just whatever fits in your memory. So yeah, this is what's missing is now putting them together. I feel like I don't have time for that, but basically what I did is now I can get different cosmological parameters from one density field because I have a posterior that I showed you in the beginning. And from these different cosmological parameters, I can now get different linear velocity fields, so that basically then I get different predictions, which will ultimately give me different density fields, or better said, it will give me the density field and the positions of the galaxies with an uncertainty that is only actually dependent on my density field that I had in the beginning and nothing else. I make no other assumptions. So this is the whole pipeline. And yeah, I think, thank you for having me.
Thank you, Constança. In fact, I see progress
Yes.
from the last time. Thanks for explaining once more that the velocity in a flow matching is not a real velocity, as others have attempted. Okay, questions. So maybe we have time for one quick question. Phil.
So in your format model, you're just clarify you're conditioning on the galaxy number density, right?
Yeah.
Have you thought about conditioning on additional parameters, if not like mass density or maybe just the color of the galaxies? Because obviously the peculiar velocities are going to be dependent upon the environmental nature of these galaxies, which we should have, right?
Yeah.
The color information.
Yeah.
Have you thought about trying to condition on?
Conditioning on mass is not super physical for us, because in the end, like having that many masses of galaxies is just super hard to measure. So for us, like what we have is redshift surveys where we measure the redshift space position of the galaxy.
It's all that color.
The color, yeah, I didn't think about that. Definitely.
Thanks.
Hi, thank you so much for an amazing talk. I learned a lot. Could you go back to the cross correlation plot you're showing for your results?
This one?
Yeah, exactly. I was just curious, could you remind me, in the cross correlation plot, which wave number do you use as roughly the cutoff for the
Yeah.
length field?
So this is the Nyquist frequency. The Nyquist frequency is E times the grid size divided by the box size. So basically it's telling me up until where do I have a resolution and values that are actual values of my simulation and not just effects of finite size effects, basically. And here this is 0.04. 0.4.
Okay, so, but the cutoff for the linear field, is a larger wave length, right?
The cutoff, here, we're only talking about the effect of the grid itself. So my linear fields are also on 128 cubed grids. So the cutoff is the same because I'm using the Nyquist frequency as the cutoff. Yeah.
Okay.
So basically, when I would go onto cubes with higher resolution, my like if I go from 128 to 256, for example, I would have double the Nyquist frequency would be then 0.8.
Nice.
Yeah.
Thank you.
All right, well, we need to move on, so thank you,
Yes.
Constança. The second speaker today is Leah Heckmann. Leah is currently a postdoc at CNRS in Paris, working in Matteo Ceruti's group. Leah has been visiting for a few weeks the CFA, and her science interest is in laser science, and you will hear, so she will be telling us about two methods, two projects, one about laser light curves and unsupervised learning, and one more fitting multi-wavelength fitting of laser data. So yeah, thank you.
Perfect. Thank you. Thank you for having me here and also having me here the last weeks.
Oh, sorry. And Leah was kind enough to bring this cert for us. So
Yes.
feel free to help yourself
Yes,
jump back.
Yes, thank you.
Yeah, thank you, Leah.
And yeah, I come from the very high energy gamma rays, so I will try to still make it understood why we are still using very old methods and now just starting to look a bit more into AI, and which is also why I'm here to learn a bit more and also maybe collaborate in the future. What I will talk about is blazars, so just a short introduction because I think there's a diverse background here. So active galactic nuclei, AGN, are like the most extreme sources we have in our universe if we look at them over a long time. So there's still some other explosions, but as persistent sources, basically they are like galaxies, or the center of galaxies, where we have a supermassive black hole that's accreting matter, that's very active, that's radiating from the accretion up to the X-rays. And then sometimes also forms this like powerful jets, so beams of radiation and particles which are accelerated away. Blazars are actually, if I look directly into the jet, if it's pointed towards Earth, which makes them even more energetic, even more powerful, even more time variable. So they really vary in time a lot, which makes them very nice to study, but also very hard to understand. Why we want to understand them is because like it's really powerful radiation and particle acceleration. So it's physics laboratories that we can't build on Earth. And their potential multi-messenger sources. So the ones which are a bit more into multi-messenger, we don't know where the messengers come from that we have. We don't know what is producing cosmic rays or astrophysical neutrinos, and lasers and other AGN are actually potential sources for this. We have been studying them for a while. We still don't understand them. We don't know what is radiating. Is it actually relativistic electrons in this jet? Is it protons? How are these accelerated? Or also in which environment, where in the jet, in which size is this taking place? There's a lot of theories, but we did make progress, but still a lot of open questions. How we look at this is in multi-wavelength studies, or also multi-messenger if we actually get neutrinos, which doesn't happen that often. And mostly we focus on single objects for one of the studies coming from the very high energy gamma rays. For example, here you can see light curve somewhere Chiron 501, which is one of the closest blazars and therefore very nice to study for us because like you can see it over like many different emission states and variations in flux. But often we actually just look at single snapshots of this emission. Often it's like, oh, it's actually here, it's flaring. Let's look at this month and try to understand what's happening there. which of course makes it not easy, but it makes it always possible to find some theoretical interpretation, but mostly not only one. It actually, like, there's a degeneracy in our models. Nowadays, we actually have quite a few of these long-term light curves. Not many if you go to AI and machine learning, but we have some. And this is, for example, over like 12 years for the whole lifetime of Fermi until 2020, but also like then sampled in radio, X-rays, and other parts. How we usually, as I said, usually what we did is like pick out certain times, often using Bayesian blocks, which is an algorithm that you can apply to one light curve, and it would tell you when you have a significant change in flux. But it would usually be only applied to a single waveband and not taking the full multi-wavelength information at the moment. Or we just do it by eye. It's like, oh, it's flaring, it's like 10 times, 20 times as higher than usual. Let's look at this time period. So now we wanted to ask the question, can we actually use unsupervised learning to better identify the laser emission states that we want to look at or that we have to understand what these objects are doing? And for this, we conducted a feasibility study using the public light curve you've seen before, but basically just using the gamma rays, not the very high energy gamma rays, because unfortunately we have an even worse sampling than the other wavebands, and the X-rays and the radio. Like we used the public light curve, so we didn't play around with the binning. We adapted the binning that was in the Fermi-lat, which is a 2-week binning, to all of the light curves. Then we scaled the fluxes, like to have the same mean and standard deviation. And basically this way constructed a 3D input set to like explore with unsupervised learning, which we have 140 data points. It's not that much, so let's see what we can get. The algorithm we choose is actually extreme deconvolution, and I have a title here, which is a Gaussian mixture model. So basically, if I have a one-dimensional data set, you can see representation of a Gaussian mixture model here, the ones in the front. So you would have like the algorithm optimizing like Gaussian distributions to describe your data distribution, and then you can assign the data points to each Gaussians, and this way get a clustering of your data. We choose extreme deconvolution because it actually takes into account covariance matrices on our input data. And if I combine different multi-wavelengths data, I have very different uncertainties depending on my different instruments. So it's very important to include these uncertainties. And it actually allowed me to do that. And there's a public implementation on it in the AstroML package. And then we used the Bayesian information criteria and the Archaika information criteria to select the number of clusters. Did 100 of runs of the algorithm for each of them to check the stability, and also did 10,000 simulations of random light curves to check what we find is significant, or if it's random light curves would produce the same patterns. Here are the results. So here you can see the results for the Bayesian information criteria and for the Archaika. And you can see it also here in the table for the 100 different runs. So each line is one of the runs. As you can see, the Bayesian one is very stable. Out of 100 times, I get 100, like a minima of 3 clusters. While for the Archaika, it varies more. So like I get more than 3 clusters, but it's more variable. If I compare it to simulations, where I basically do the same thing, but on the random light curves, I actually, out of the 10,000 times, only get 6 clusters 6 times. So I actually, like, it's only a 0.06% chance that this would happen randomly. While for the Archaika one, it actually is like a 3% chance. So it's not the most stable result. But we wanted to try both to see the influence of it, especially since it's still a very limited data set. The result that you can see here for the light curve, so this is the minimum of 3 clusters. We reached very stable with the Bayesian information criteria. And you can see here the different fluxes. So on top, you have the gamma rays, here you have the X-rays, and here you have the radio. And what we can see is that it very well selects by X-rays, which is also where we have the biggest variability. So we have a high X-ray cluster, more intermediate one, and here a very low state. It's also nice because exactly the same low state we identified by doing a Bayesian blocks on the very high energy gamma rays, which are not actually in here. So it confirms some of the previous results, but it would allow us to at least get a rough idea of the emission states. It still would be nicer if we would have more divisions in the flaring states, because we know usually it's more variable. what happens there from what you see also in the spectra. But for this, we also need a bigger data set. If we compare it a bit more in like the 2D spaces, so the correlations between the different wavebands, here you have the gamma rays versus the X-rays, which usually are also very correlated. So we see, okay, we have these 3 clusters. While if we look at the gamma rays versus radio or the X-rays versus radio, we see more complex patterns. So it's like, if you would look at this without colors, it would be more of a blob. But if I now color it, you can still see that in different spaces, I have the clusters that I see. And this is also interesting because we usually know that part of our radio emission doesn't come from the same region as the X-rays and gamma rays in lasers. We know it already from modeling and also from radio images that part of it's actually further along the jet than we have in the X-rays and gamma rays. So this way, if we can extend on this study further, it would be nice to identify which part of this emission is maybe coming from which part of the jet. These are the results if I get 6 clusters with the Kaikke, which, as I said, we can trust a bit less. But here you also see it a bit nicer that actually while in these 2 spaces, the clusters are not as distinct. Here it really clusters by X-ray versus radio flux. Where for the lower X-ray fluxes, I would also divide in lower and high radio fluxes. Sorry for the box in the back. What we also know from like the study before is that actually the rate, if we like look into correlations between the wavebands, the radio usually comes with a delay to the gamma rays. So it's like first we see a flare in the radio, which then around 100 days later shows up in the, first in the gamma rays, then in the radio. So what we now tried is repeating the same thing, but shifting the radio back. So we would correct for this correlation. The patterns we get actually by eye don't change too much. But we are now looking a bit into how we can quantify if it really improves things or not. So as I said, usually we look into correlations. So if we see that 2 bands are tightly correlated, the emission is coming from the same region at the same electrons. While if it's less correlated, it is less. And so we actually now computed the correlation in the form of the discrete correlation function. It's just a measure taking a bit more into account. It's a bit like the Pearson correlation factor. Just a bit more adjusted to our kind of data. And then we like computed it for all clusters and then for different combinations of the clusters. And here you have it for the gamma rays versus radio and X-rays versus radio, ones without the shift and ones with the shift. And we can see that the correlations actually with the shift also improve between the bands where we didn't see it before. This we now want to quantify a bit more, but as I said, it's a feasibility study, but if we actually put in more data and more information, it would really maybe help us to see, okay, actually, these 2 are very tightly correlated, while this one is making a bit of a random thing, just as an idea. And this brings me to the conclusion on the first half of the talk, which is that actually, like, we see that we can get something out of it. Of course, it's still a very limited data set, but we see distinctive clusters. And we see that it confirms previous results, like the low state that we found before, or also that radio shows a more complex pattern. At the moment, there's just a proceeding on it, but we have a paper in progress. And one of the bigger plans where we also might need input and help is to actually get a bigger data set. In this case, we probably know where to reach out to get X-ray, UV, and gamma ray fluxes. We have to see how many places we can include, but probably like, I guess, 20 to 30. With hopefully similar sampling. The problem, a big caveat is I need simultaneous data points. And then we can actually test different binning options or also unsupervised learning techniques and improve a bit on what we can find. And this would be nice because on the one hand, we can study for each laser which emission states we have and how they change and what changes. Also taking into account not just fluxes, but also the spectral information or how the flux changes. But we could also maybe see between different lasers, which emission states do we have only for certain ones and which we actually have about for 10 lasers in our sample and they are recurrent. Maybe I'll stop with questions on this part of the talk before I go to the second.
I have one. So could you, for those who are not familiar with this, could you explain a little bit the difference between the BIC and the AIC?
Yes. So basically with the BIC and the AIC, we are looking for the minimum of the log likelihood. But if you think about a polynomial fit, if I just order add degrees of freedom on a fit, like with the most degrees of freedom, I can always describe my data best. So we need to put in a penalty for the degrees of freedom that we add, and they are just penalizing in a different way. So the big penalizes a bit stricter, while the AKIK penalizes a bit less strict on the added degrees of freedom. So like the added degrees of freedom in my case is the number of clusters. So yeah, because otherwise it would always like to find 114 clusters because it's easiest to describe my light curves. Yes.
So we're applying gas emission models. So,
Yeah.
okay. And how are you passing in the data? You've got these 3 different wavelength bands and blocks of information.
Mhm.
Are you also giving it time?
No.
No. So you've just given
Exactly.
blocks and wavelength.
And I can't go back, but yes. Yes, exactly. And this is also the nice thing, because you see it in the clustering, that even so I don't give time and I don't do it on purpose. So on purpose, I only give the fluxes, not the time. It still clusters them together in time. So it still shows that there's a connection. And also it's the first method that can actually tell me that these are recurrent. Because usually a Bayesian block would just tell me here there's blocks of data, but it would not relate this to.
To me, it looks like it's splitting on Swift X-ray.
Yes, missed, but it's also the most variable in our band. But not just, as you can yeah. But also, yeah, this is 3 clusters, so then it's.
I have a question, but I think it's kind of related to Dan's one. So you say that they have to be evenly spaced to split the pulse into the model. Is that
No, they don't need to be evenly spaced. This is the next thing I want to try. I now just use the public data set, so that's why it's binned in 2 weeks. But I actually want to try adaptive binning to get the most amount of data points.
Yeah.
But it was just the first try.
no.
Good. Then I'll now move from the light curve space to the spectral space of lasers. So usually if we then select one of these time periods, what we do is create an SCD, so the spectral energy distribution of our lasers. So trying to understand with our models what is happening in this time period. The way we do this is we collect multi-wavelengths data as before. And then we construct flux points. I mean, a lot of people working with X-rays are also doing the same or probably similar things. So for each different instrument, so for the UV one, for the X-ray one, for the gamma ray one, I'm taking my count data, my event data, and then I'm fitting a simple function, usually a power law, to then get a flux point and an SCD point. Because it's just a very limited energy interval, I cannot fit a more complex model. And then, so for example, here, these are the flux points I get. They are all from different instruments, and then I combine them together, and this way we model our data. And then we apply physical models. Here you can see 3 different ones for lasers. Lasers always show these 2 bumps that you see, either by fitting processes or sometimes also by eye if the models are too complex for fitting processes. But of course, because I do it in the flux point space, I add a bias because I assumed a simplistic model of a power law before, which is not really what I see in my data at the end or in my model at the end. And this we demonstrate here. So this is a demonstration in X-spec. So it uses a black body. So basically, I just have the temperature and the density of my radiating particles. I simulate an X-ray spectra. And then I do both things. First, I fit back just by a black body on the events, on the real counts data that I have, which gives me the red fit with the 1, 2, and 3 sigma contours. And then I do the same, but at the bias that we usually do. So I first assume a power law, reconstruct flux points, and then fit it to the flux points, which gives me the blue one here. And we can see that it adds a bias compared to the 1, 1 space. And this is what we now want to investigate and also hopefully correct on a multi-messenger basis. So not just multi-wavelengths, in the future also taking into account neutrino information. At the moment, multi-messenger using gamma pi. Gamma pi is a Python package for gamma ray astronomy. It's basically the modern version of X-spec for gamma rays, which takes different gamma ray data, mostly very high energy gamma rays, but also, for example, Hawk or Fermi, puts it in a common data format, so event lists and instrument response functions, so characterizing the energy dispersion that we have or the point spread function. And then you can use the package to get sky maps, spectra, or light curves. Nowadays, it's also been expanded to use it for X-ray and UV or down to optical, not as part of the package, but as an add-on package. So here you can see a multi-wavelength fit. Here you have gamma rays, X-rays and UV, all done inside gamma pi on the events. So not on the flux points, even so we show it with flux points because we cannot really show the events too easily, fitting it like this. And this is now what we want to use to actually enable in gamma pi that you can put in just your theoretical model for your blazer or also other sources, and then apply it to the data or without adding the bias of the flux points. So we're building on this workflow. Then we are putting the instrument response functions of the different instruments into gamma pi. We are using real data or simulations, so we can use UVOT, XRT, and Fermi, so also UV, X-rays, and gamma rays, which are public data. We have simulations for the next generation of very high energy gamma ray telescopes. And these inside gamma pi then allows me to simulate data, which I can then really investigate which of our methods is working and which is not. So I'm actually simulating data using this IRFs based on the real physical model, which I later also want to fit. And this is, for now, a leptonic self-synchrotron model, which is the simplest model of a blazar, but it really describes the physics that we would expect if it's a leptonic model. I'm using a public code called chatset, which applies this model. And then we can also easily include systematics inside gamma pi, or also reddening and hydrogen absorption via the Sherpa module for XBAC, which you can also include and link. If we do this, we can simulate data sets, and I simulate 2 data sets. The first one is actually the real data set that we would get if we had observations, so event and count data. The second one is I do the same experiment as before. For each instrument, I fit a power law on this data and then reconstruct flux points to add the bias that we would usually get if we follow our traditional approach. And here you can see the results. Here on the bottom, you see an SCD. Don't worry in the back, it's not that important anymore since we don't use flux points to really fit. And here you can see the results for a model with 5 free parameters. And in green, you can see the fits on the first, so really on the events and counts. And in violet, you can see the flux point fits. And you can see for most of them, we are like always having the bias to the violet flux point fits. So we are seeing the same as we saw before in the black body. And also we see that it actually converges nicer because 5 free parameters for this very limited data points is already quite nice. It's still not good enough because we usually have like 8 to 14, 15, but this we need to constrain by the physics. So it works quite well and it shows better convergence, but the event fits of course takes longer, 5 to 10 times, which in this case, it's not a problem. Like chatset runs with 0.02 seconds for one realization. If we have more complex models like hadronic ones, which is really important for the multi-messenger nature, it increases to 1 minute instead of this. So this we cannot run on the fly. So now we are looking into grid models, and this is where later on also machine learning will hopefully help us, and interpolation. So at the moment, what we're doing is producing a grid of our models, so like over an energy grid, but then also over the parameters that we have, playing around with how many grid points we need at the moment, and then just interpolating. So I produce a grid of my model for like all of the 5 parameters you saw, or actually more. I produce a grid, and then I take the SciPy regular grid interpolator to like tell me how my SED would really look like, which works well enough, at least for this kind of SED. There have been shown that there can be some problems, so you can see it here. And it works well from a physical point. So I can reconstruct, I mean here, sorry, different colors. My events fit is orange now, and my flux point fit is blue. And at least for the events fit, I'm always in the 1 sigma region from what I can constrain. But but of course, it's limited by computation time and also especially memory usage, as you can explain. Like imagine if I have an 8-dimensional grid put into memory. And this brings me to my summary. So actually it works quite well to enable this as a first try, which helps us to reduce bias and to be able to reach better conversion of our models and take into account absorption or systematics very naturally. But we're still limited by a large amount of free parameters that we have. And especially well it works for fast models where we can just fit on the fly in gamma pi. We tried also different minimizers. The user can then decide what's best for the model and try it out. At the moment, Minui is a bit preferred because, for example, we also tried Bayesian nested sampling, but Fermi-lat data is actually a bit complex to fit because you have more free sources and then it takes a long time. For slow models, we have a big problem. So now we are trying it to grid models, which show already now as the first try, show us some of the computational resources will not be enough. And this is also where I will probably bring it to the hands-on here that we will look into neural networks or other machine learning models that might help for this, and then look into how it could be incorporated in this paper. And yeah, with this, I want to thank you, ask for more questions, and there's cake.
Thank you, Leah. Questions for Leah?
Yeah.
Yes, that.
You had a plot before showing flux-based bits and count-based bits for this one, yeah, that one. It seems like you're getting very different information from the counts and flux-based bits.
Yeah, I think it's just because of Minui, how it explores the parameter space. It doesn't explore the full parameter space because we would expect like these correlations should look the same, and they don't. And it's just how much of the parameter space is explored by the minimizer.
Okay, so it's not like you're getting extra information
No.
from one or the other.
At least not with the simple methods.
Do you have one? No? Oh, I thought you had a question. Any other questions? So you said two things. You say you're simulating this data and you're hoping that the machine learning methods could help. I guess they could help either by emulating some of the ones that are very slow, so you could
Yes.
try to. But then you are also trying to. You also said that your nested sampling MCMs is too slow, for which something like normalizing flow model or
Yes.
something could be a good replacement. Have you thought about? Well, I guess my concrete question is: do you trust your noise model for these predictions? Do you
Yes.
understand well what the noise is in the instrument so that you can generate?
I get the noise from real data, except for maybe the very high energies because it's not public, but I get the noise from real data, so I trust it, at least for these kind of places.
And you can add those data sort of estimations of the noise to your simulated
Yeah.
your simulations.
Yeah. So I basically use real data, I load real data into gamma pi, which is basically the event split and the IIFs. Then I just take the IIFs and simulate new data based on the model. So the
Great.
noise is in.
Forward to hear more of the AstroAI meetings in
Yeah.
the future. Thank you very much. And if there are no more questions, thank you, everyone. We have another talk in another week, and please help yourselves to some cake courtesy of Leah. Thank you.